So our next speaker is Alok Ladha. He is from Chennai Mathematical Institute. He will tell us about positive geometry of non-planar S matrix.
Okay, so this is the title, from positive geometries to scattering amplitudes. If you don't know some of these words, don't worry. Hopefully in the talk I will explain. Since this is kind of a gift to Bal, I hope he goes easy on me during the talk. So yeah, so this almost all the work I'm going to talk about is done with a student Brunmai, who was at CMI, but now he's at Caltech. But really, most of what I will say is based on a large body of other works which has been done in past, especially past 5 years. All the names in reds are physicists and all the names in blue are mathematicians. So there is a kind of 50-50 split into this contribution in this field. Let me start with some basic motivation for what the whole program is about. So, most of us know that S matrix in quantum field theories come in many different representations. The most standard one, sorry, the pointer is not working, is the one on the top, which is the usual field theory approach that we see in books. We can also call it off-shell approach because we work with fields and we can have off-shell propagators, etc. But then there are other representations of the same S matrix. The one which is probably second most popular is what is called the on-shell recursion, where you never go off-shell, but you allow momenta to be complex. And then there are some other ones. For example, there was a one pioneered by Parmeshwaran in the 80s, which was about recasting S matrix in gauge theories and gravities in twistor space, and many others. So it's the same S matrix object, but we can write it in many different forms. The final answer is the same, but at the intermediate steps we see different structures emerging, and these are different representations because they make different postulates manifest. Manifest, and some things emerge. So, for example, in the usual Feynman diagrammatics approach, we never compromise on unitarity or locality at any stage in the computation. But there's a price to pay that because we go off shell. There is some intricate analytic structure, and we see some singularities which are not always physically easy to understand. If you always stay on shell, like in BCFW, then unitarity is always preserved, but locality is not manifest. So in the intermediate steps of computation, you may seem like some terms come from some non-local theory, but it's kind of a myth, mirage, in the sense that in the end, the final answer is of course some local S matrix. And if you work with this worldsheet approach, which has been quite, which was formulated almost 10 years back, which is recasting S matrix of a local quantum field theory in terms of worldsheet, like in string theory, then neither unitarity or locality are manifest, and they kind of emerge only in the final answer. So it's a bit of a mystery that what function defines on the space of external momenta what we would call kinematic space an S matrix. So it's clear from this table that if different representations sacrifice different postulates, none of these postulates are probably truly fundamental in defining the S matrix, and maybe all of them are derived from some deeper set of postulates. So for a long time, people thought that unitary and locality are very fundamental, but now we understand that that's not necessarily true. So okay, so we can recast the question which is written in the block as what are really the core hard postulates of the S matrix program that can never kind of be compromised, and from which all the other postulates can be sort of derived. And another maybe more grounded way to ask the same question is, when do we know that if we are given a function in the external space of external momenta, when do we know that it classifies S matrix of some local and unitary quantum field theory? So this is one of the the sort of the dreams of this program that I'm going to discuss in this talk, is to sort of discover core postulates from which all these other postulates emerge, and in some sense seek a more fundamental representation of the S matrix, from which locality and unitarity emerge. So I want to keep just this. This is of course a very ambitious sounding goal. So I just want to keep this in the mind to put the talk in the proper context. And so just to set up some notation, we are going to work with scalar, S matrix, which is going to give us amplitude for scalar theories. So our kinematic space is simply space of external data, which are going to be governed by some isometries of space-time. So to be very specific, we'll work with kinematic space, which is associated to Minkowski space, where the external data is just the Mandelstam invariants. And there is an interesting basis for these Mandelstams in this kinematic space, and it's a very simple algebraic relation that if you define a object which I have called xij here, where you order your labels from 1 to n, let's say in clockwise fashion, and define Xij as given here, then Sij, any Sij can be written as a simple linear combination of these Xij's. And so this will be important for us later. Okay, so now this is the, so I'm just going to give you a very broad picture of where we will head in the end. That, if we only have access to Mandelstam invariants and nothing else, how can we start classifying functions that represent amplitude? So we don't want to start from a theory, or we don't want to assume unitarity and locality, but can we still somehow isolate functions which are S matrix of some theory against functions which are not? And so what we are going to do is sort of, as you will see, that the first thing that emerged in our classification is this singularity structure of the S matrix. In the sense that we will see that there is a nice geometric interpretation of the singularities of the S matrix, and they're going to be boundary of a very special class of geometries that are in mathematics literature called positive geometry. And there is a more sophisticated definition of positive geometry in algebraic geometry, but for our purpose, it's enough to define it like this: that it's any geometric object which has boundaries of all codimensions. So if you start with a segment and it has two endpoints, then it qualifies as a positive geometry. But a circle is not a positive geometry because it should have a boundary of, it should have a zero-dimensional boundary, but it doesn't have. So the idea is that what we will see is that there is this class of geometries which are just sitting there in Mandelstam space. So all we have to do is find them, and once we find them, they are going to lead us to a large class of amplitudes for theories which are going to be local and unitary. But okay, the first question to ask is, why should we look for some specific class of geometries at all? And so, okay, we have to start somewhere. So let's say that, whichever representation of S matrix we work with, there is some combinatorial structure which is common to all of them, which is basically graphs. So, if you are working with, if you keep Feynman expansion in mind, if you are working with tree-level amplitudes, then you have graphs which are without any genus. But if you have loop amplitudes, then you can think of them as graphs having loops, genus, etc. So, we could ask the following question: is there a geometric structure that one can associate to arbitrary graphs? Now, I just want to emphasize that we will not use any prior knowledge of Feynman diagrams, because that will defeat the purpose. So, because we don't want to assume anything. So all we are assuming is that we start with some combinatorial structure which are graphs, and see how much we can build from here, what kind of geometries we can build from graphs. And so here is a nice fact that, if you take, for example, any tree-level Feynman graph. So again, these graphs are just, there are no momentum labels to them. They are just combinatorial structures. So to each tree-level planar graph, and if suppose it has only cubic vertex, then we can associate to it a triangulation of a n-gon, as shown in the first figure. So I've drawn some 6-point graph, and dual to that 6-point graph, which when it has cubic vertex, is this sort of a dissection that I've drawn in the picture there. In fact, what I've drawn is very general. 2 vertices are cubic and 1 vertex is quartic, and it still dissects the polygon into 2 triangles and 1 quadrilateral. And in fact, what is probably not very well known is that we could even do it with graphs which have genuses. So if you take, say, 1 loop Feynman graphs, and let's say for simplicity we only look at cubic vertices, then one can associate to it a triangulation not of the usual planar n-gon, but of a 2 n-gon with a hole at the center. So if you look at the figure on the right, you can check that triangulation is dual to a 1 loop graph, which is shown in the red on the right hand side of the figure. And this fact is related to some other theory in mathematics, which was discovered by 2 mathematicians in 2015. And this is a very general structure, in the sense you give me any 1 loop graph with cubic or quartic or any vertices, I can always associate to it a pseudo dissection of a 2 n-gon of the type that is shown there. So these are some combinatorial structures that just emerge out of nothing in some sense. As soon as we are given graphs, we can just draw them. And here is a very beautiful and a known fact in mathematics from long time, that if you consider a set of all triangulations of a polygon or an n-gon, they can be glued together systematically in a single object, which is of dimension n-3 if you are working with n-gon, and it's called a Stashev polytope or associahedron. So I have given 3 examples here. So if you just look at triangulation of a triangle, which means no triangulation, it gives you a point. If you look at triangulation of a square, there are 2 possible triangulations, and you can go from one to the other by just 1 flip. So they are, connected to each other by 1 line. And if you look at triangulation of a pentagon, then there are 5 possible triangulations, which are the 5 vertices of the pentagon. And the interesting fact about this relation is that if you go from any one vertex to adjacent vertex, you always do one flip of one diagonal and keep other diagonals intact, as you can clearly see from the picture there. And it turns out that this structure is in fact true even for pseudo triangulation. So if you consider all these pseudo triangulations of a 2n gon, like the one that is drawn there, you can exactly with the same principles, by flipping one diagonal and keeping everything intact, glue them together into a specific combinatorial object, which for various purposes is called d hat polytope. It's a polytope of dimension n if you start with an n gon. So I've just drawn here a d hat 2 polytope, which is really a hexagon, which is associated to a graph which has two edges and one loop. And in some, I mean, if you keep the fact in mind that every triangulation is dual to a cubic Feynman graph, this is already, I would say, a kind of a remarkable fact that these combinatorial objects, package all the tree level and one loop graphs of phi cube theory in a coherent relationship. So you have a million diagrams in phi cube theory, and they're all packaged together in a single geometric object. So here I've shown a three-dimensional associahedron in this picture, and you can see that all the triangulations are glued together in a nice way. And mathematicians call them mythical polytopes because they have very interesting properties which are not generically true for polytopes in that you draw, like simplices. So for example, every vertex of this associahedron or the d hat polytope is adjacent to the number of faces, which is same as the dimension of the polytope. So as you can see in this first picture, every vertex is adjacent to three faces. So if you look at if you look at the topmost vertex, it's adjacent to two pentagons and one square, if you just stare at it for a while. And this is just generically true even for the d hat polytope. So this class of polytopes are called simple polytopes because knowing the dimension means you know the adjacency number of every vertex. And here's the property which is even, I would say, more remarkable, that if you take any lower dimensional boundary of this associahedron or d hat polytope, here I just wrote it because of lack of space for the associahedron, then it factorizes in terms of lower dimensional associahedra. So what it means is the following, that if I look at the associahedra up to dimension 2, I have either a point, a line, or a pentagon. And so if I look at any two-dimensional boundary of a, let's say, three-dimensional associahedron, which is the lower figure, it can be either a pentagon or a square. And square is okay because it's a product of two one-dimensional associahedra. But it can never be a hexagon because you can, a hexagon is not a two-dimensional associahedron and it's neither a product of one-dimensional associahedron. So this is a very rigid structure which constrains the geometry of associahedron. Okay, and I mean, you will obviously ask, I think Bal would have asked that, at this stage, what's the relation with physics? And there is really at this point no relation except the fact that, every vertex of the associahedron is dual to a cubic planar graph. But that's just that's just a tenuous link in some sense, nothing very deep. You can do the following thing. Now you can associate to every of this so maybe here. So if I look at the two triangulations which I've drawn here, 1, 3 and 2, 4, I can associate a real variable to it, which I'm just calling x13 and x24. I mean, the labels are self-explanatory because it connects the vertices between 1 and 3 and 2 and 4. And you can think of them as, there's a useful parallel between these labels, which have actually nothing to do with physics, and the basis we chose in kinematic space, which was these capital X variables, which we could have written really in terms of this, so capital X13 will be P1 plus P2 square, which is very similar to what, which is exactly the propagator which will flow in the second diagram. And similarly, if you associate a variable, say y, so let me just go back. If you associate, let's say, a variable, if you look at this guy and associate a variable y to any one of the arcs, you can, it's a useful parallel to think because they are dual to one loop graphs. You can think of these y's as coming from some loop variables. I mean, we'll see this more precisely as we go on. But if you are getting impatient about physics link, you should keep these things in mind, that this chords of the dissection can be thought of as dual to propagators of some Feynman graph. Okay, but so far it's only combinatorics, and there's no way we would get anything like S matrix. from such bare combinatorial structures. And so obvious question is, to get S matrix, we should have some sort of dynamics at least. And in fact, it turns out that there is a discrete dynamics built into the definition of these polytopes. And it's what is called a mutation rule. So I give you a qualitatively example first. So the example shows a mutation where you keep all the other chords fixed, but you just mutate or flip one of the chords ij to a chord kl. But of course, to implement these dynamics, I have to tell you what is the configuration space on which I'm implementing these dynamics. And it's natural to understand what the configuration space is, because we can associate to each chord of an n-gon, for example, a real variable. And for an n-gon, there are n into n minus 3/2 number of possible chords you can draw. So that's the dimension of the configuration space. X's are all real variables. Similarly, if you take a pseudo PT just stands for pseudo triangulation. So if you take a pseudo triangulation of a 2n-gon, then again there are n square number of possible chords you can draw, and with each such chord we can associate a real variable. And the labels indicate you go from where to where. So ij means you go from an external vertex I to j, and I bar means you go from, maybe it was here. So this is one example. So when you write xi, it's the chord which is going from 1 to the to the left of the annulus, or from 1 bar to the right of the annulus. If you went the other way, like if you drew a chord from 1 to the right or 1 bar to the left, that will be x1 bar. And xii bar is just draw an arc which goes from I to I bar, which I haven't drawn here, but I hope it's clear. So you can associate to all possible chords you can draw one variable, and that's the configuration space on which we will define some kind of a dynamical system. Yeah. No. So that's just a mirror image. So x1 bar is when you just switch them. I haven't drawn it here. Yeah. So you connect one to the right and 1 bar to the. Okay. So now here is a mutation. Here is the dynamical equations we can put on this configuration space. So for example, in the case of planar triangulation without the hole, every time you do a flip, so you go from ik to jl, put this as a equation. I will just tell you in a moment where these equations come from. The equation is very simple to understand. xik plus xjl, which are the initial and the final flip, minus whatever chords were adjacent to them. So I hope from the figure it's clear. The vertices ijkl bound the quadrilateral, and that kind of tells you uniquely what this equation is. It's kind of a discrete equation on these x variables. And if you solve this equation, which was shown by these mathematicians in 2019, they span a convex polytope. And the reason they were interested in equations is for the following reasons. It's a complicated subject, so I'll just try to give you a flavor. So you can ask why mathematicians consider this equation or these geometries, and that's for the following reason. That let's consider a pentagon. I'm sorry, my figure is a bit crappy. Let's just consider this pentagon here, and let's draw this arc, which is just a completely, I'm going to label that arc as 2, 4, because the first vertex is adjacent to 2 on the left, and the final vertex is adjacent to 4. Now you can associate to this red line a vector which depends only on the intersection number of or intersection nature of these two things. So I fix 1, 3 and 1, 4 as some reference arc, and given that reference, I can associate collection of 5 vectors which sit in a plane, which I have drawn there. So the assignment is the following: if 2, 4 and so I'm calling this red arc 2, 4. If 2, 4 and 1, 3 intersect in a Z shape, I assign a number -1. And you can see that 2, 4 and 1, 4 intersect in a -Z shape, so I assign a number +1. And with that assignment, you can see that you get these 5 vectors. And these 5 vectors have a remarkable property that they completely span R2. And in fact, you take any 2 vectors which are adjacent to each other, they each span a cone. There are 5 cones here, and these cones never intersect except in their boundaries. So this specific object is called a fan. And the question the mathematicians asked is that what is the polytope whose normal faces are these normal vectors are precisely these vectors, and these equations give you that polytope. So that was their motivation. That there's more behind it. I'm just giving you a very small sketch. So now let's systematize this more concretely. and it's the entire structure is completely universal. So you fix any triangulation, say T naught, or a pseudo triangulation that is called PT naught, and then these mutation rules give you following set of equations that you consider all the chords which are neither in T naught nor in PT naught, and put all the all the variables you get from such chords, where Yij is defined like this as the last equation. So put all such y's to be constants for all the reference chords. So you can check that this precisely gives you these all possible mutation equations and give you convex geometry that you can draw in your configuration space. So here is a striking result that was proved by mathematicians in 2018 and 19. So this was proved for triangulation by mathematicians, and then we generalize it to pseudo triangulation, that for any choice of this T naught and PT naught and any arbitrary choice of this positive constant C, the solutions of these mutation equations always give you convex realization of either the associahedron or d hat polytope. And this convex realization has another interesting property, that it always lies in the positive quadrant of your configuration space. So you don't have to look at the whole configuration space, but you can just look at this positive octant. So let me just give you one example. You can look at, let's say, a reference triangulation, which is the one that I've drawn there. And then, oh, sorry, I should not. I mean, you could just work this out and you would get a interesting realization from here. So for the associahedron, these were derived by physicists actually by looking at some, I mean, they kind of knew what answer they wanted based on the theory of amplitude, and they wrote down some equations, but it was consistently integrated into mathematics into the series of papers later. Okay, so here are some examples. So for example, if you start with 1, 3 and 1, 4 as a reference of a phygon, you'll get the first picture, and that's the two-dimensional associahedron that you that comes out of solving these equations. And the three-dimensional realization is the one that is drawn in the second picture. And both of these have an interesting property that precisely n-3 pairs, n-3 is the dimension of the polytope, are parallel to each other. So in the first figure, you can see that two pairs are parallel, two faces, like 1, 3, 2, 5 and 1, 4, 3, 5 parallel to each other, and 2, 4 is the only one which is like an anomaly. Yeah, so the associahedra, the way they were drawn, I mean, because these equations were first discovered by 4 physicists, Arkani, Ahmad, Bai, Hay and Yan, so they are called ABHY realization. And similarly, the d hat realizations were first discovered, without some rigorous arguments by Arkani, Ahmad, Say, Salvatore, Thomas, so we will call them AHST realization. So when you see this superscript, they just tell you that, these equations were first discovered by these authors. So we have so that's why we call them ABHY/AHST polytopes. So all the associahedra are the ABHY realizations, and all the d hat are the AHST realizations. So I have given you one example of this two-dimensional d hat 2 polytope in the lower figure. Okay, and now here comes so as we saw that all these positive geometries live in a positive octants of the embedding space of this Xij space, Cartesian space, and so they all have boundaries which corresponds to Xij equal to 0, where Ij can be any chord. So in the case of the triangulation, Ij will be some chord connecting external vertex I and j, but in the case of pseudo triangulation, it could be also one of these arcs that we were drawing between I and the annulus, or I and I bar, etc. Now there is a kind of an interesting result in algebraic geometry, that all these positive geometries have an interesting property that they induce a unique top form. So if the dimension of this polytope is d, then they induce a unique d form, whose rank is same as the dimension of the geometry. So here is the top form on the ABHY realization of the associahedron. So okay, the form looks a bit abstract, but let me just explain the notation. So it's a sum over many forms, where where each term in the sum is corresponding to take all the, so T is a triangulation. So given a triangulation is spanned by some chords, like collection of chords Xij's. So you take product over all the Xij's and you sum over all such triangulations. So as a concrete example, I have written a two-dimensional top form for the associahedron. So there are 5 triangulations, 1, 3, 1, 4, 1, 3, 3, 5, 2, 4, 1, 4. So there will be 5 terms in the blue parenthesis, and there is the basis x13, x14 comes from the fact that to define this associahedra, we have to fix a reference T naught. So when we drew this top associahedron, the reference triangulation we fixed was 1, 3, 1, 4, and that dictates that the coordinate form that we end up with is dx3 which dx13 which dx14.
You define the algebra.
Algebra for
You say gentle algebra.
yeah, no, I didn't get time. So these realizations that mathematicians discovered. Sorry, let me just go back. So these have you can think of these realizations as coming from representation of some class of algebras called gentle algebras, which really arise from. I mean, if you look at these triangulations, you can associate to them some quivers, and those quivers give rise to some class of algebra. So there's a whole theory behind this one slide, which I didn't, go into detail. Yeah, and so it turns out, yeah, since you asked, I just say that, in fact, we discovered a new class of quivers and corresponding representation theory, which we just call them colored gentle quivers in the case of the pseudo triangulations, which some of mathematicians not interested in these before, so they didn't find them. Okay, and similarly, we can define top form on this d-hat polytopes also, and here is one example. So it's the same idea. You take any vertex of this d-hat polytope, which is like pseudo triangulation, product over all the arcs of that pseudo triangulation, which is xij in the denominator, sum over all the vertices, and then there is a reference pt naught which we have to choose, so that gives us the coordinate form. So here is the example, and so I just repeated what this xi and xii bars for just from before. Yeah, so the form, just to recall, in the case of association, this form is sum over all possible triangulation, and so this should already tell us that there is some connection with amplitudes is emerging, because we know that triangulations or pseudo triangulations are dual to Feynman graphs with or without loops, and it turns out that one can wonder where these coordinate forms come from. So that is just a choice of the reference we choose. So if you choose a different reference, instead of t naught you choose, instead of 1 3 1 4 you choose 1 3 3 5, then the coordinate form will be, oh, suddenly a light came. Coordinate
Dual to some vector fields or just algebra?
No, these forms are actually, you can think of these forms as defining volume of the dual polytopes. So these polytopes, you can associate with them some duals.
But then you have to integrate.
Yeah, and that.
What are you integrating? So they have to be contracted with vector fields.
Yeah. So the vector fields are the coordinate vector fields because we have chosen this basis, right? The Cartesian basis xij's. So those are our vector fields. Yeah, yeah. But okay, you can still see that there is some connection with S matrix, but still no real sign of S matrix. And of course, there could not have been because there is no physics so far in any of these variables. These xij's are some abstract variables that we associated to our choice of chords, etc. So okay, so now yeah, just recall a little bit, and then we go to S matrix immediately. So we started with some very basic topological observation that any tree level or one loop, Feynman diagrams are dual to dissections of some planar n-gon or some 2 n-gon, and the specific set of these dissections defined for us a dynamical system whose corresponding equations generated some polytopes, and then algebraic geometry, some results told us that there are some specific forms that we could define on these polytopes. So that's what we have so far, and it turns out that these forms as they stand define what is called, I will explain this in a moment, planar S matrix of a class of already scalar field theories which are called bi-adjoint scalar field theories. So they are scalar field theories where each scalar have two adjoint indices and only cubic interactions. So that people who are familiar with Young-Mills amplitudes know that once we fix color of the external states, only planar diagrams contribute, and that is why, as we will see in a moment, that this the stuff that is multiplying dxmn, that function already gives us amplitude of some theory. So that theory is this particular theory. So let me explain how that happens. So this is now where we make the connection with S matrix explicit. So far the small x was just some, the small xij's, if we collect them in a vector, it was some vector in this Cartesian space, as Bal was asking what was the vector field. So it was either, in the case of the associaedra, the dimension n into n minus 3 by 2, or the dimension was n square of this configuration space. And but we already know that there is a nice basis in the kinematic space of Mandelstam invariants, which is this capital x13, x14. So now we can see that there are sort of two Cartesian spaces of same dimension with different bases. One is the usual physics basis, which is the capital Xij, and one is the totally abstract small xij basis. So we can ask, okay, what are the possible maps that we can define between these two bases, and that will give us connection with the physics. So the simplest map you could look at is just identify them. So you just say that small xij is capital Xij for all ij, and then it turns out that if you do this identification, then the function that was multiplying the basis form in the case of the ABHY associator gives us a planar amplitude for this phi cube theory, bi-adjoint phi cube theory. and the function that was multiplying the the basis form in the case of d hat gives us the one loop integrand for the bi-adjoint phi cube theory again. So we already got some interesting physics out of this very trivial identification of these two spaces. But of course, this is not, there's nothing that chooses this map. We can choose infinitely many GLN maps between these two Cartesian spaces. But the next question you can ask is, what is the map you can choose which doesn't depend on any other external input? And the obvious map, okay, so sorry, here is one example of this MN1 loop, just to illustrate that, if you compute this form in the case of d hat 2, you get the usual radiative correction to the propagator and two Tedpol terms. Okay, I'll skip that comment. So now we can ask for more general maps. Now the only maps you can think of which do not use any other input is the following. So you associate to the small xij, not capital Xij, but a permutation over the labels I and j, which is indicated in the first equation. If the permutation was identity, then it will give us this trivial map that we started with. But it could be any other non-trivial permutation, and in principle that's a good GLN map. And but notice that if you have a permutation which is cyclic, then that's a trivial identification again, because if you just have a cyclic permutation, then you are just relabeling your indices in the same order. In the same way, if you look at a permutation which maps 1 to n to just changes the clockwise orientation to counterclockwise, so you go from 1, 2, 3, n to, instead of that, to 1, n all the way to 2, then the set of small xij's don't change under that permutation. So these two are trivial permutation, so we have to sort of quotient them. So if you quotient them, you get this set which I am just calling it Gn, and the cardinality of Gn is what is written there. So now the idea is that if we look at all these maps instead of trivial maps, do we get some interesting S matrix in the kinematic space? So here is the if you do this for n equal to 4, so you had one ABHY associahedron in the abstract space, which is this line, and if you had used the identity map, then it would give you only that associahedron in the kinematic space. But if you use three possible these maps in G4, sorry, you will get these two more associahedra. So you in the case of n equal to 5, you get 12 different associahedra that you can draw from these maps. And so now the question is, what do all these quantities give us? Now one interesting fact here is that the other two, the green and the blue one that we obtained, from the physics perspective, they have poles at u equal to 0 and s equal to 0, or u equal to 0 and t equal to 0. So it appears that somehow this collection of all these images of associahedra has all the poles of the S matrix, not just the planar poles like in the bi-adjoint theory. And so it turns out that in fact by looking at all these associahedra, we get the full S matrix of phi cube theory, not just the planar. So let me just explain that quickly. So here's a simple counting, but it was an interesting identity that we discovered, that if you look at the number of vertices of the associahedra, that's this what is called a Catalan number, and it's a known result which we can derive from induction, that total number of tree level Feynman diagrams with only cubic vertices is this 2n minus phi double factorial, and the cardinality of this group Gn is n minus 1 factorial by 2. And here is a nice identity, that the total number of diagrams give you the size of the group times the number of vertices of the associahedron divided by a factor 1 by 2 to the n minus 3. So if we could somehow show that when we scan over all these maps sigma, if each vertex repeats equal number of times, then we can use this identity to write the full S matrix as follows. So here's a theorem we could prove that in the set of all the, so you take your ABHY associahedra and you look at images under all these F sigma maps for all sigmas, then each configuration or each propagator configuration is repeated precisely 2 to the n minus 3 times. And so then so here is the exact result, that you look at the push forward of this canonical form by all these maps and just divide by a normalization, and that gives you the phi cube S matrix. So this is an interesting fact, that the the ABHY realizations, the simplest one we could come up with in the kinematic space gave us the S matrix of phi cube theory without color, and we to define this map we used no external input. The maps just came from the fact that we could relate Xij to the only thing we used was the fact that we had a freedom to not identify Xij with capital Xij, but do the first equation in this area. Yeah, so I mean this sort of fits into this what I call amplitude-hadron ideology, that somehow we have a positive geometry for a S matrix of a theory which is ordinary phi cube theory. So far it's tree level, yeah. And so now, but you can immediately ask, why did this happen? I mean, how did we get a function which has the property that we expect of a S matrix, which is, for example, unitarity and locality? And so I'll just quickly try to explain why that happened. So first, just recall that every face of the associahedron corresponds to some chord, erasing some chord ij, or in other words, putting xij equal to 0. And it turns, and this is a property that we kind of reviewed in the beginning a little bit, that any boundary of associahedron of codimension 1 is always product of two lower dimensional associahedra. And the algebraic geometry result told us that this form has simple pole at all of these xij's, for all ij. So the third statement is really a statement of locality, in the sense that when we go on shell, we get simple poles, right, at the propagator, when we take some propagator on shell. And because of the second point, which is the specific boundary structure of associahedron, you can show that if you take xij to 0, so you go to some boundary of associahedra and look at the residue of the form, it factors into lower forms on these associahedra, which is precisely the statement of unitarity when you go on shell. So it's because of this structure of these geometries that we got, unitarity kind of emergent from this. Okay, I'll skip this. There is some interesting connection of this with the worldsheet picture of the S matrix. And how much time I have?
Exactly, another 5 minutes you get.
Okay, cool.
Break of 8 minutes.
Yeah, no problem.
Where is the phi cube coming in?
So it just, I mean, that's the result we obtained. So if we just write this down, this is exactly the S matrix of phi cube theory. Yeah, and it came reason because we looked at associahedra, which come from triangulations which are dual to cubic. I mean, that's the. Okay, I have 5 minutes. Yes. Oh, okay. Then, okay, in general, let me just quickly go. I mean, you could have considered now more general class of mappings. For example, you could look at GLN maps and some translations. And then, if you do this and you start looking at, we have so far only investigated simplest class of maps where this G, boldface G is like a diagonal matrix, for example. And so here, this table, maybe the first table is a little bit illustrative, that if you look at, okay, so if the second row is G's identity and there is no translation, as we saw, that gives us just a colored S matrix. If you consider G1 to be a map of this type, which is written in this box, so think of small xij is alpha ij, xij minus mij square, where alpha ij's are some specific numbers, then it gives you S matrix of a theory which has one massive scalar field, one massless scalar field, and they have some specific couplings. So, just by looking at various ways we can embed the ABHY geometry into kinematic space, we start getting a whole class of S matrices in quantum field theory. And these are giving us planar S matrices, but when we compose these maps with the sigma maps we defined, we would get, the full all-in-colored S matrix of this theory with one massive, one massless theory, etc. And so, okay, I'll skip this. There is an interesting example where we could look at a, Yukawa type coupling, and then we could run the mass to infinity, and we get some interesting geometrization of effective field theory. And okay, so now you may think that, okay, looks like we are only doing cubic interactions, but we know that, any set of poles of any higher point scalar interaction is a subset of the set of poles with cubic vertices. So, the question we can ask is there a way that this ABHY associahedra and this D hat n generates S matrix with other interactions, let's say 5 to the p interaction? And this was already in some sense answered by mathematicians in this very beautiful paper in 2017, where they showed the following picture, that, if you look at these dynamical equations we wrote down, and you project them onto any subspace of Xij. So for example, you just pick one chord and project the equation, look at only those equations which are projected onto that chord. It will always give you a convex relation of some combinatorial polytope, which are known as accordiahedra in the case of the n-gon, and pseudo accordiahedra in the case of this 2 n-gon with the annulus. And so here is an example of this projection. So you start with your associahedra, in the as shown there, and then that's a 3-dimensional associahedra, and you project it on one of these faces. So there are two possible projections I have shown. One is a square projection, and one is a pentagon projection. And these are polytopes in their own right. And it turns out they give us 8-point amplitude in phi 4 theory. And so the one can actually, we proved that the complete planar phi to the p S metric is sum over all such projections. So everything comes from ABHY or these AHST polytopes. Okay, so here is kind of more or less a final answer, that a dynamical system associated to dissection gave us some convex realizations of some combinatorial geometries and some forms, and rest is only either linear map, GLN map, or some projection. And here is kind of a small dictionary we could write down, that if you want massive poles, then you just shift the entire geometry. If you want many fields, you have to rotate it using this GLN. And if you want to have higher point interaction, then just project the polytope into some, along some boundaries. Okay, so I think that I'll skip this. So at the very least, I think I've showed you how to annoy Bal in less than 30 minutes, even if you didn't get anything else from the talk. But there is a way I know how to unannoy Bal, because he likes beer. And so here is a way we can please Bal. So these other members of Bal fan clubs, one of them is sitting here. And so happy birthday, Bal. Yeah, so I only showed you, yeah, just let me just go back to the d hat. Yeah, so this form, for example, the first line gives you the one loop integrand for the biadjoint phi cube. And then we could do the same, this what I told you, you can do these projections. So you get these polytopes whose form give you one loop integrand for biadjoint phi to the p, for example, theories. So they only give us integrands, they don't give us the final answer. Yeah.
Fermions?
Yeah, no, actually.
You cover coupling or something.
Yeah, in some sense, fermions were thought of before in the amplitude-hidden picture, because of the fact that that was a supersymmetric theory. In general, I don't know. I think one has to go to spinor helicity space to include fermions. But fermions are the higher spin particles. I think has not been done in non-supersymmetric case yet.
So if I take the phi cube theory,
Yeah.
I can think of the amplitudes, for example, as coming from the tachyon vertex operators of an open string.
Yes.
theory.
Yes.
And there the amplitude then eventually reduces to an integration over the moduli.
Yes. Yes.
Is there any way
Yes,
I can
yes.
think of that moduli being connected to these
Yeah,
polytopes?
it's actually very precisely connected through the CHY formula. So the world sheet that you get in the alpha prime going to zero limit is this moduli space of punctured Riemann sphere. And if you compactify it, then you get combinatorially it's once again an associahedron, but it's a curved associahedron. And now it turns out that, but it's an associahedron. So you have associahedron on that side, on world sheet side, and you have this ABHY associahedron. And the scattering equations, which is what you get from the alpha prime to zero limit, is a diffeomorphism. Yes.
Using that, they were able to do the connected with knobs, the loop things in point.
Yeah.
Again, they are using only graphs, the tree graphs.
Yeah, I agree. Yeah. Yeah, I mean, there is some work in that direction, not my work, but there is some work by Claude Dour, etc., who are using. So what Cohn et al., as you are saying, did was that they discovered that if you look at 1pi diagrams, they have this Hopf algebra structure, and you can associate some polytopes to the, so you can associate some geometry to that Hopf algebra also. So that has been explored now by people, they have revisited, but to my knowledge, it has nothing directly to do with this geometry. That still, I think we have to still.
Question is about fermions. Can you put fermions? The second question is, this is only if there is a mass gap. If there is massless particles, there are many supersymmetric sectors.
Yes.
And so this works only perturbatively. Am I right?
Yeah. So this is so remember. So this gives you either the tree level amplitudes or the integrands, and because we are doing scalars, we are agnostic about space-time dimension. So it gives us integrands, in d dimensions right now. So right now we don't know how to deal with, I mean, I can tell you more privately, but right now as it stands, we don't know how to deal with the infrared issues that you are mentioning. Yeah.
It's again to do with the perturbative nature of this. I expect phi cube theory to be unstable.
Yeah.
So where would you see the instability?
No, that's an excellent question. So I mean, it's metastable in some sense, depending on the strength of the
exactly,
coupling.
yeah.
Yeah, I think we will not, I mean, we have to do again the analysis of the resound S matrix. At this level, we will not see it. No, it's a very good question, I think. The geometry itself so far doesn't show us the instability. I agree that it should show eventually, but
I think the problem, dangerous question is the instability is because the Hamiltonian is not bounded.
yes, yes.
But there is no Hamiltonian in this formulation.
Yeah, no, this gives us a volume of a polytope which match with the S matrix of phi cube theory.
Doesn't give you evolution equations for Cauchy data.
No, it does. It just gives us S matrix.
So that doesn't define the physics.
No, S matrix define a lot of physics, no?
Lot of is not the same as all of. Lot of is not the same as all of.
Okay, that I would agree. Absolutely, yeah, not all of.
Yeah, I have a question. Why is bi-adjoint scalar?
No, so that was again, the point is that if we looked at the most simple map, which was the just identity map between the small x, capital X, we could ask, is it giving us, it's giving us some function of P1 to the momenta, is it amplitude of some theory? So you could now go back and check, is there a Lagrangian you can cook up? And the Lagrangian you come out with is this theory where you have scalar F2 adjoint indices and cubic interaction. So.
Other cases of fundamental, bifundamental and all this.
No, actually there is work. So actually if you couple, for example, this bi-adjoint scalar to a bifundamental scalar and look at Yukawa type coupling, they are coming from what are called open associahedra. So people have found them also, but they are a bit more subtle to define than this. Yeah.
Okay, if there is no further question, already everybody is hungry. I think we should
Thank you.
leave it. Let's thank Alok again.